Hello, everyone. Welcome to your weekly webinar from the APS topical group on data science. Great to have you with us if you are either new or if you are, like a person who has been attending for some time. So one moment while I right, so we've had several webinars that we have presented in the past, ranging from an intro from Patrick Riley to last week's tutorial with Jason and Alexander. So we have an upcoming event on data science education next Friday. So please join us for that. It should be exciting. Our previous chair, Mohammed Saltina, will be presenting in that, and so it should be a really good time. For those of you who are not yet following us, then here is an opportunity to follow us on social media. You can either look at us, you can email us at gds@aps.org. You can also join us on our Slack channel. And we even have a YouTube channel now where we are posting previous videos. So today you're in for an all-star treat where we'll start off with some lectures on Gaussian processes given by Valentin and by Dan. Following this, then you'll get to work on active learning in an experimental context with Gilad. And then we'll move more towards the theory and modeling side with Boris and with Jonathan. So as a bit of introduction, one moment while I try to minimize my screen. Okay. So Valentin is a research scientist at the University of Maryland. He's been very active in applying machine learning and AI to materials. He received his PhD from Johns Hopkins University, and before that, he was a postdoc at Argonne National Lab. Jonathan is now a physics graduate student at Harvard, interested in condensed matter theory and machine learning. Boris Kozinsky is a professor, at Harvard, where he leads the Materials Intelligence Research Group, and he's also working on developing computational methods for designing new energy materials using machine learning. Gilad received his PhD from Carnegie Mellon University. He's a staff scientist at NIST. And an adjunct at the University of Maryland. He has been working on any number of projects in the machine learning space and autonomous systems. He also has been involved, not just involved, but was one of the founders of a workshop and boot camp on this very topic. So he'll tell you more about that later. Dan Samarov is a statistician at NIST. He received his PhD from the University of North Carolina at Chapel Hill. He is in our statistical division at NIST with interest in machine learning, bioinformatics, and non-negative matrix factorization. So I will be posting various links in the chat window to let you know where the various Python notebooks are, These videos will be going up on YouTube, so you will be able to refer back to them. Also, as a bit of housekeeping, if right now, if you are in the audience, which is now 73 strong, then if you have a question, there is a question tab. So we will be monitoring the questions, and either we will let the presenters know that you have a question and read it, or we will unmute you so you can ask the question yourself. So if you have questions, add them to the question tab. This will be interactive. Also, one other bit of housekeeping. Both of our presenters will be using either the Google Colab or they will be using Jupyter Notebooks. So the advantage of this is that you don't have to install any software on your machine and that everything can be doable in the browser. In the course of doing these, we've realized that some people are not familiar with the Colab. And so I'll just give you a few slides to show you how to interact with it so that you'll be ready once our presenters start. And so, if you see, if you open a Colab, if you see a Jupyter notebook or a file with a .ipynb ending, then you'll just double click on that file. And if you have never started the Colab before, you'll get an option to connect more apps. You'll want to choose that option. And then, yeah, so, or actually first you'll get an open with option, and then you can choose connect more apps. One of the apps will be the Google Collaboratory, so you'll choose that, and it'll open up in this nice web-based browser. But you won't be able to actually modify it because this will not be on your local Google Drive. So in order for you to interact with it, there will be a little button you can click called Open in Playground. So you can choose that option, and that will let you work in a sandbox mode where you can just play. So if you click that, then you can run through everything. You can also save it to your local Google Drive, but to make things easy, just choose to open it in the playground for now. So let's see, with that, I think we are about ready to start. And there is a question about, could we post the links here? I will post them in the chat channel as we go along. And so you'll be able to just click on them. So if you are having trouble, just ask a question and we will be with you. So with that, I believe that my portion is done. Just again, remember, follow us on Twitter, join our Slack, and if you would be so kind to join us as part of the American Physical Society topical group on data science, we could always use a little bit of funding that comes from that. So with that, Jay, can we switch to Dan, who's going to lead us off with an introduction to Gaussian processes?
Let me know when you guys can show my screen. All right. Let's make sure. Yeah, the format is going to be an interesting and new one for me, since the questions will largely be to myself, at least at the beginning. I want to make sure that everybody on who'll be presenting, you guys can see my screen. Is everything up and running as it should be?
It looks good here. You'll probably want to maximize it though.
I mean, it's about as as it can be. So yeah, I'll because I'll just be bouncing back and forth between this and Colab.
All right, sounds good.
All right, so normally we really love to have this be as interactive as possible. So with that being said, please post questions in the chat, and while I may not be able to respond to them directly, the other panelists and presenters will be able to. I'm going to kick things off by introducing Gaussian processes, and later we're going to be learning about active learning. A little bit of humor for your Friday, given all that's going on here. Some of you need a chuckle. So normally, and this is a little bit of a pitch for a boot camp that we run in July/August, and we're going to see how some of that may need to be modified with everything that's going on. This usually falls kind of in the middle of a workshop we run on machine learning, where we've had a chance to talk a bit about supervised learning to kick things off. So some of this may kind of be moving things at faster pace than what we ideally might want to be doing. And again, if questions come up, don't hesitate. Feel free to reach out on the chat, and if you need to be unmuted so you can ask me directly, definitely feel free to do that. These slides, I believe, are going to be made available to you all, so information on the workshop is going to be there. We're big fans of it. We've loved running it for the last couple of years. We've seen it grow every year. It allows us to take what we're going to be covering today and to take a really, really deep dive into kind of all the areas of machine learning, from coding and getting comfortable with Python. We have a day that's dedicated to that, to hands-on data processing, feature engineering, a day dedicated to supervised learning and unsupervised learning, and then some hackathons and such, so that you can kind of get your teeth sunk into some of these things. And here's just some additional information. So diving right in. One of the things that I think is really important to understanding really any area of machine learning is that these things are all super interconnected. I think a critical building block, and something I'm going to kind of point back to throughout our lecture here, is tying the intuition back to something that we're all, or maybe it's an unfair generalization, but most of us are quite comfortable with, and that's thinking about linear models and linear regression, stuff that we learned in our Stats 101 course, and seeing that these more advanced topics are, in fact, in many ways, direct extensions of those things. And that is accurate when we talk about Gaussian processes or neural networks, and really anything in between. So where I want to kind of build things from is, again, this intuitive starting point of linear models. And for most of you, this form where we're saying we want to relate some outcome, our y's, as a function of our inputs, our x's, and we believe that the appropriate relationship between those two things is some linear combination of those inputs, our x's, weighted by some beta, which is telling us about the relevance or importance of that particular input relative to an outcome. So in this particular setting, we have interpretability. We kind of can look at and understand how, as we change a particular value, one of our xj's here, how that impacts our outcome. Now, extending this to neural networks, and this is something which is going to be a little bit hand wavy, and I'm going to just have, for now at least, for you all to kind of accept this as truth, is neural networks are just kind of an extension of this, where rather than looking at this kind of clean form here, we abstract it through some appropriate basis, a phi of x. And you can think of this as like a polynomial expansion of our x's, is one example of phi. When we're talking about neural networks, though, the actual form of this mapping, mapping phi here, is a little bit more intricate. But ultimately, the intuition still holds and still connects back to this more familiar form of a linear model. Now, one of the things that we might be interested in is a more general form for our function f here. In both of these cases, whether we're talking about a linear model or we're talking about neural networks, we've assumed a parametric form for f. Now, in some situations, we may want something which is a bit more general. And so that's where Gaussian processes come in. And so there we're essentially kind of flipping things around, and we're saying, let's assume that we're trying to find some f that appropriately characterizes our data. And part of the learning process is actually going to be learning the form of that function. And the natural question is, of course, how is it that we can kind of go from sampling a multivariate Gaussian or a Gaussian process here where we have assigned a mean 0 to the process, so this is a vector and some covariance matrix K. How do we go from sampling this multivariate Gaussian to actually sampling a set of functions, something that's going to be relating our inputs to our outcome? So the first point, and it's just something that I think for most of us who've worked with data before, maybe done some simulation, we're comfortable thinking about sampling random data from some distribution in 1 and 2 dimensions. So when we're sampling a univariate Gaussian, we might expect the distribution, if we were to kind of plot a histogram of it, to fall along this well-known bell-shaped curve. Now, the idea is that as we move from 1 dimension to multiple dimensions, that this bell-shaped curve just kind of changes appropriately. In 2 dimensions, it becomes a mound. In 3 dimensions, it's a sphere. And past that, it's kind of hard to visualize, but the idea remains. And so, of course, looking at this by itself, again, not immediately obvious how we move from that to sampling a set of functions. And so we're going to kind of spend a little bit of time here, because I feel like when we've taught this before, one of the big sticking points that we've encountered is really moving people from how it is that these random draws from a Gaussian relate to a space of functions. Now, for most of us, again, if we're thinking about sampling, say, like a 2-dimensional Gaussian, the plots that we have here on the bottom are going to be a pretty familiar picture. So just to kind of give a little bit of context, each kind of row is getting progressively more correlated. So these are just 2-dimensional Gaussians we're sampling from, and the only thing that's changing is we're just increasing the correlation between the points. And you can kind of see that, at the bottom one here, that things are kind of stretched out, and we see, a strong correlation between our x1 and our x2, whereas on our top left plot, things are just kind of random. By the way, can people see me moving my mouse around? Because I'm moving it to kind of point to things, and I want to make sure that that's visible to everybody. Can one of the panelists let me know?
Yeah, we can see it.
Okay, great. Okay, so each one of these is just a 2D Gaussian. So the question is, how do we go from any single point in here to a function? And so this is going to be kind of our first step in building that intuitive building block. Now, the first critical point to really, hit home with, to nail home, is we need to first assume that there's an ordering to our axes, to the dimensions we're looking at. So normally, when we're sampling from our multivariate Gaussian, in this case, our 2D Gaussian, we have an x1 and x2. There's no sense that x1 is greater than x2 or less than x2. But when we're thinking about this in the context of sampling from a space of functions, that point is really critical to understanding how each one of these can be in fact thought of and looked at as a function. So here we're now going to assume that our x1 might be, say, day 1, and our x2 might be a day 2. And the values that we observe in here could be temperatures or stock values. So kind of connecting this more directly, let's take this point here, right? And so we're going to look at its value for day 1, which is about, around 2. And we'll plot that value. So this value here corresponds to day 1 with a value 2, and that again could be some normalized temp. And then we're going to look at x2 or day 2 here, and we're going to see that that value is a little less than 1, like minus 0.5. And so that's this pink line here. Okay, so this, albeit not a very interesting, is a function, right? It's a function with just 2 points, but the critical point here is that we have an ordering along our axes, so day 1 and day 2, and the value here is what we're looking at on our y-axis. Are we seeing any questions yet, by the way? from the audience, or so far so good?
So far, so good.
Okay.
Oh, you do have a request that you move to the presentation view, just because some people are finding it difficult to read the smaller print.
Yeah, I apologize. Normally this is on like a large board, so I'll put in a presentation. I don't know that I'm going to have time to get to my notebook because I want to make sure that Valentin has an opportunity to get through his material, and I know that we're already about 15 minutes in. Okay, so hopefully this is a little bit better. Now, taking this one step further, really just to drive home the point, now let's introduce an additional dimension. In this case, again, remember that we're preserving an order to our axis. So this normally, if we're just thinking about generating, multivariate normal points, this might be x1, x2, and x3, but here we're thinking about ordering as being an important part of what we're looking at. So this would be, say, again, day 1, day 2, day 3. Each value in here would be some normalized temp, again, just as a use case. And now we're plotting these each out. And so you can imagine that as we add more and more dimensions, that we're going to see kind of more features and behaviors in here that are looking more like a actual function. This is a movie that doesn't work, unfortunately, but what this is meant to illustrate, and just kind of tying back to our 2D case where we were increasing correlation, is that one thing to kind of note as we transition between these plots is that in this first one, these lines, or again, I'm going to use the word function just to drive the point home, are really quite variable. They're all over the place. They're not necessarily kind of trending in the same or similar directions. But as we increase the correlation between them, we see that the difference between our day 1 and day 2 values decreases. And that the reason for kind of revisiting this is that we're going to kind of switch the way we talk about this from having a high degree of correlation between, again, here x1 or day 1 and day 2, to thinking about this as introducing a degree of smoothness between our points. So my slide seems to be stuck here. I don't know if this will, nope. Okay, good. All right. So now all we've done is taken the previous set of examples and generalize it from 2 and 3 dimensions to, in this case, 200. Now, again, each one of these might be a temperature that we're observing over time. And the way that we're generating each one of these curves is, once again, sampling from a multivariate normal distribution, where now we are saying that the dimensions themselves preserve or have some sort of meaningful order to them. And we have our covariance matrix, and the covariance matrix is the thing that's ultimately driving the smoothness, the kind of behavior that we're observing in here. And touching on what I just mentioned in terms of increased correlation being connected to increased smoothness, at least between proximal points, that's really kind of coming from this matrix here. And so we're going to look at a couple of examples. I'm going to kind of just breeze through this slide here, and it'll be available for reference. One of the high level kind of point here is that tying this back to, again, another area that some of you may be familiar with neural networks, that as it turns out, you can show that for any given layer within your network, if you let the number of neurons within that layer grow to infinity, that they begin to behave like a Gaussian process, or behave as though they've been instantiated with a Gaussian process prior, which is what this particular prior is for our space of functions F. Okay, so the question, of course, becomes, how do we go from generating this random set of functions to having something that actually fits our data? And let me just check out where we are here. So the first thing that we're going to need to do is we're going to need to take our assumption about the prior in terms of how we believe our data generally behaves, and we think is sort of an appropriate fit to the types of features that we might expect to observe. So here, this is just some simulated data that is, just a dummy use case for building intuition. We need to take the data that we've observed and update our assumption on the prior distribution associated with our data to arrive at a function or space of functions that now captures both our initial assumption and has been updated now with the data that we've observed. And this just boils down to good old Bayes rule. And any time that we talk about anything Bayesian, we have to have our de facto definition of what Bayes rule is. Here, this represents our posterior distribution. So our set of F's updated with the data that we've observed. This is our likelihood function. So this tells us about how likely this data would have been generated given this particular function. And then this is our prior, and this is a normalizing parameter here, this P of D. So this, for those of you who've done anything with Bayesian inference, should be pretty familiar. But ultimately, the thing that we're really trying to get at when we're doing any form of Bayesian analysis is this posterior distribution. So updating our prior assumption with data that we've observed. As it turns out, with Gaussian processes, we actually have a nice closed form distribution for this particular prior. And when we update our prior with data, we get this particular form for our mean and this particular form for our variance function. Now I'm going to jump over to Colab since it seems like I do have a little bit of time. And I'm just going to pause there again just to check with the panelists to see, do we have any questions yet? How, or so far so good?
So far, no new questions.
Okay, great. So hopefully some of you are going to be able to follow along here. Again, the benefit of doing this in a workshop environment is we can kind of go around and help people troubleshoot, but we can potentially do that offline as well as people want to kind of run through these examples. So the main module that we're going to be using here is called GPy and GPy opt. These are kind of the one of the more commonly used Gaussian process libraries that are out there. Here we're loading up a number of helper functions for visualizing our data and manipulating it. And again, for the sake of time, I'm just going to kind of breeze through this. There is a specific use case that we have here, or example that is definitely more on the Polymer side. For those of you that are interested, here's kind of an explanation, also a link out to the Git repository. So I'm going to kind of go through and start running each of these so that we have everything loaded up, and hopefully this won't take too long. Uh-oh. So it looks like I may need to actually reinstall this here. If this is taking too long, I might just, oh, no, looks like it's going pretty quickly. Well, hopefully some of you are able to kind of follow along in real time then. And while this is loading, we do have some visuals in here, so I'm just going to kind of skip ahead. All right, so I'd mentioned that the kernel functions are sort of at the heart of this, and Valentin is going to take a deeper dive into what each of these are, which of them are appropriate for the different types of problems. And I don't want to steal any of his thunder, but just to kind of go through these, a few of these examples here and illustrate what some of them look like. I will kind of show just what some of the different types of kernels, how they relate to the set of functions, the space of functions that we're ultimately sampling from. Here is probably the most commonly used or commonly well-known kernel, which is the radial basis function. The plot that we have here on the right essentially is capturing how similar we want proximal points. So if I was to look at, say, row 50, this would be, say, day 50 in the example I'd given before about temperature. And as we kind of traverse along this row, the blue points are closer to 0 and the yellow points are getting closer to 1. And each one of these is a weight basically showing how similar a given point might be. So if we're looking at point 50 and here 1, we can see that the weight between these two, the relationship or the amount of information that we want point 1 to convey to point 50 is pretty minimal. But as we kind of move along here, we can see that we're having more and more influence from, say, point 25, point 30, 35, in terms of how we want it to influence and ultimately generate these functions that we observe here. So this is effectively just a large covariance matrix, and it's telling us about the proximal similarity between points. As we kind of increase this window width, this kind of yellow bar would get wider and wider. Or it depends on how the radial basis function is parameterized. If it's smaller, then this becomes might become wider and wider. Again, it's important as you're kind of playing with and fitting these different models that you look at how the library actually kind of characterizes each one of the kernel functions. Okay, yeah, it looks like here as it becomes smaller, you can see that the weight or the area in which we allow a point to be influenced by its surrounding points gets smaller. And again, we're making it smaller here as well. Okay, let's see if our library finished loading here. Okay, looks like we're all loaded up. And everything came together just fine there. And hopefully this just makes it more convenient to access the data. We're just pulling it directly from the GitHub URL. Again, a little bit of an explanation. As mentioned at the beginning, I am not a polymer scientist, so I won't try to explain what's here, but you can always kind of look out at the reference to get a little bit more background and context. In a visual of the data we're going to be looking at, we're going to start again with like a simulated example as a starting point. But we're going to come back to this one. Well, I don't know that we'll have time, but if you work through the notebook, we'll start off with a simulated example at the beginning, and then toward the end, you'll see that we come back to this particular data set. Here's just a helper function for generating and looking at Gaussian processes. And then I'm not going to run this just because it takes a little bit of time. Actually, it shouldn't be too bad. So I'm going to rerun this. Essentially, all that we have is a whole bunch of different types of kernel functions that come built in with this gpi module, which is really nice. And we're going through and just visualizing each one of these and what's there. Again, you can kind of see that each one of these is going to be capturing different types of features associated with the data. And one of the, I'd say probably, or arguably one of the biggest pieces of using Gaussian processes boils down to your choice of kernel function. And I think that that's probably a good point to transition over to Valentin, since I know that he's going to be talking about kernel selection and parameter optimization. So thank you all. Again, please post questions in the chat, and now that I'm off, I'll be able to respond to them. So thanks so much.
All right, thanks a lot, Dan. I don't see any questions yet in the chat, and so, oh, okay, we do have a question. And so this is from Christoph Toth, where his question is, okay, his question is about basically whether or not this is the APS 2020 Gaussian processes, or it looks like there's an A version floating around as well. If either Valentin or Dan can type the current version, a link to the current collab in the Slack, then that will be useful. The one that I have there now may be a slightly out of date one. With that, let's see if we can move.
Where should I paste that? Should it be in the chat? I just want to make sure I'm putting it in the right channel.
Yeah, in the chat window, and have that go to the entire audience. Meanwhile, we will try to move the presenter over to Valentin.
Hello,
Okay,
can
so
everybody hear me?
you're perfect.
Okay, great. So let me go to presenters mode. Okay, so yeah, my name is Valentin Stanev, and I'll be doing the second part of this introduction to Gaussian processes. And I'll talk, I mean, Dan presented, gave a theoretical introduction and how you can think of them. And I'll go over some more practical questions. So how do you actually work with them, and you know, how, if you want to use them to do some particular model, what are some of the things that you have to do? So this was where we got with Dan, and so you had this general idea of so you have some functional space, and then you have points, and then you use these points to constrain the number of functions that not the number really, but there are still infinitely many functions, but you can constrain the class of functions that go close to your data points. In the good thing about this is that you don't only get one function, some kind of nonlinear function, but you in fact have an infinite number of functions, and this gives you some idea of what is the uncertainty of your model, what is the you know, what would be a reasonable fit and what would be not so reasonable fit, and that is great, and it sounds a bit abstract. So just to make it again more specific, you know, what really is going on if you want to. So you can sample this functional space, but what is really going on is that, for example, you choose a point, let's say somewhere between -2 and -1, and then for this point you find what is the your fit, the mean of your fit, and then for each point you basically you have a Gaussian, and you can sample this Gaussian. So it's under the hood, you have you still have a multidimensional Gaussian, and the only thing that makes it interesting really is the fact that you have this covariance matrix, covariance function. Otherwise, if it was 0, you just have a bunch of uncorrelated Gaussians. Uncorrelated Gaussians seem to be like a white noise. So what really gives you this function is the covariance function. So this is the non-trivial part of this model. Now, so in a way, the covariance function, also known as kernel function or just kernel, is really is your model. It encodes your assumptions about the function that you're trying to model, you're trying to learn. And there are many kinds of kernels. This is the most probably the most commonly used one, which is called the squared exponential or radio basis function. It has, and the thing about it is that it has some hyperparameters. So these are things that the way we were doing it before is that you fix them by hand before you do the actual modeling. So this is probably the most intuitive one is the length scale, which, so this entire function tells you how are different points in space connected, what is the strength of their correlation. So if you know the function at point x, what can you tell me about the function at point x prime? And you see that this is like exponentially decaying function. So and the length scale is L, which means that if you go beyond this length scale, basically you don't really know much about this function at x prime. If you're closer, then yeah, sure, and of course it goes to 1 as you know, it goes to some fixed value as L goes to 0. So, but this is an important parameter. And as I said, the way we have been doing it so far is that these parameters are fixed. And I've added also I've added a noise term because if you, especially if you're dealing with real experimental data, you would expect to have these typical measurements have some noise. So maybe your measurement is a bit off. So you have to take this into account. So we have hyperparameters. But the point is that so this is a little bit about these hyperparameters. So as I said, you have different length scales, and the classes of different functions that you get with different length scales can change a lot. So this is, if you have a length scale of 0.1, you have this kind of rapidly varying function. It's still smooth because this isn't. It has this smooth form, but if you look at on this length scale, it looks like very rapidly changing. If you look at the same window, the same fixed window now, and the length scale is 1, you see that you have this kind of smoother thing. And of course, if you increase it further, you get even slower changing function. I mean, this sounds intuitively clear. We understand. I mean, this is a function that every physicist would understand very well. So it doesn't. It sounds simple and clear. The point, however, is that once you fix this length scale and these other parameters as well, they have a really important. They have a big impact on the model that you get. So these hyperparameters is not something that you should fix once and then forget about them. They do have an impact on your model. And this is, for example, what can happen. So this is an example that I got from this book on Gaussian processes. It's available, it's free, it's available online. So you should definitely, if you're interested in Gaussian processes, this should be definitely one of your standard references. By the way, I do get this messages that I have some connectivity problems. Do you guys hear me? Is everything going
so far? No
okay?
problems. Yeah, so
Okay,
far everything's going great.
You're great.
Okay, thank you. So so I'm modeling the same data points, but then I'm having different length scales. So you see that if I have a length scale which is really short, I get a model like this, and it's okay. You can say, okay, that sounds good in the sense that it goes through all the data points. But if you look at it, you see that it's kind of strange. I mean, it's really very it has all these wiggles in it, and you would say, well, it's kind of weird. I mean, do I need to have this thing? I mean, how would I support this? From the data, would I expect this? Of course, there is a huge uncertainty because you're allowing very many functions. So you can have a function like this, but you can also have a function like this, or here you see this kind of you have this huge uncertainty in what is going on between the data points because you're allowing functions which wiggle a lot. So it's a model that is good in the sense that it passes through all your data points, but it's a bit too flexible. I mean, you have all this, and the result is that you have these big uncertainties, and that's something that you would like to avoid. Now this is the opposite limit. So now you're choosing a length scale which is way too long, way too large, and now you have a function like this, and then the model is trying to, and it just cannot pass through all the data points, and the model is compensating this by assuming that you have a very large noise. It says, okay, you fix the length scale, now the result should be that you have a very large measurement noise. So your measurements are very kind of far from the function that I can fit, and also, it might be the situation. This depends really on your data and your understanding. But if you, for example, if you look at the residuals, you see that the residuals are correlated. Residuals here are on this side of the mean function. The residuals on this side are above. So I would say, okay, that's if you look at the residuals, you would say, okay, that's probably not a good model. It's a bit too constrained. So in kind of conventional language, you can probably say this is overfitting, this is underfitting. All the people that do Gaussian processes don't like that language very much. So you just say that this is too flexible and this is too constrained. And this is now the model which is just right, and of course we know that because this is how the data was generated. And it is not it goes to all the data points, so in that sense it is a good fit, but it also it doesn't have so many wiggles, so you also the uncertainty between the points is small, because it's you're not assuming that you have like a huge you're not exploring that the functions that you're exploring are constrained, so they cannot change too much. So this is an example of a fit which seems to be it's a good fit. It's not too flexible, it's not too constrained, so it is just right. Now, of course, if you have a simple function with with one dimension, then you can do that by just looking at it, and you can tweak it. But that's not typically, of course, we have higher dimensional data. It's not a very efficient way of doing things. You just go back and forth and tune it by hand. So is there a way to learn that these hyperparameters, not just set them by hand, but try to learn them in some a bit more kind of automatic way, and more principled way. And the way to do that is so we still have this machinery of likelihood functions. So this is again continuing the same example. Imagine that you have higher dimensional square exponential, or RBF kernel.
So Valentin, we have a question actually.
Sure.
So the question is from Jonathan Dietz, and it's, why is overfitting and underfitting not appropriate terms to describe this behavior?
So okay, the way why people doing Gaussian processes don't like this is, okay, let's go back to how do I go back? Sorry. Okay, so so what would be a definition of overfitting? Well, overfitting is something that gives you a much higher error on your test data set. So this is now we are thinking about the standard way of doing things. So you have a training data set and you have a test data set, and then you have a model which for which the test error is much higher than the training error. Now here it may not necessarily be the situation, because you see you have this huge uncertainty. So the error here is probably small, but then even if your data points are even if you have some test data points somewhere in between, you see this huge uncertainty. So your training your test error may not necessarily be so much larger than the training error. So this is why people it's probably not a very appropriate way to talk about overfitting. So the model is flexible, just like in overfitting, but you have this uncertainty. So you don't, I mean, it looks like overfitting if you look at the mean function, but in fact your model is not only the mean function, you have these huge uncertainties. So if you have a point here or somewhere here, you can easily find a function permissible in your model which goes to there. So it's not crazy. Whatever you do in between is going to be okay with your model. So in that sense, it's not it can fit in between. It can fit anything. So that's why it's probably not the best language to describe it.
Jonathan, is that okay? Oops.
Yeah, that's clear. That's clear to me. Thanks.
Yeah, thanks for the question. Yeah, that's a good question. Okay, so now let's go back to sorry. So we are still using the same kernel function. It's just now we assume we have a higher dimensional space, so you can in principle have different length scales for different dimensions. It doesn't have to be the same. You can of course postulate it's the same, but it doesn't have to be. And now how can we actually optimize in some way these hyperparameters? And the way to do it, I mean, there are different ways of doing it. This is a bit of a shortcut maybe. So it's not the most principled Bayesian way of doing things. If you're doing the full Bayesian thing, you have to define hyperparameters and then you marginalize it. And this is in principle, it's a way to avoid all this, worrying about overfitting, underfitting, and that stuff. Here it's not. It's somewhere in between, in the sense that we are not defining priors, but it's still a way that takes a bit of this worry about having too flexible a model. It is a natural way of balancing the flexibility of the model versus how well you fit the data. So this is the marginal likelihood, and it's marginal likelihood because you can think of it of this distribution. So this is the probability for your data, given your axis, where x is what are the x coordinates, and y is basically your measurements or your data. And you can think of it as it's marginal because you can think of it as integrating all possible functions that are permissible that within your model. So you've integrated all your model, all your functions, and you have this distribution. And as I said, at the end of the day, it's still basically a multidimensional Gaussian. So that's the beauty of this. You can do it analytically. You can do a lot of things analytically because you have just a bunch of Gaussians, and that's pretty much the only integrals that you can do is just Gaussian integrals. But now this is, if you think about it, this is now a function of the hyperparameters. So you can take this marginal likelihood and optimize it. Find them. You want to. Typically, of course, we do the log likelihood because it's easier to work with logs. You can actually maximize the log likelihood as a function of these hyperparameters. And if you just take, this is Gaussian, so you can immediately get this point, these two terms, and then some constant. And it turns out that this is basically the prefactor, the normalization factor in front of the exponent, and this is just the factor inside the exponent. Now this has nothing to do with the data. This is just has to do with the model that you're constructing. And this is a term that is connected to model capacity. So how many, how constrained is your model? And this is the term that has to do with the data fit. How well is your model actually fitting the data? And it's not obvious, it's not trivial to see this, but this is what's going on. And it turns out that, of course, these terms work against each other. So if you want a very flexible model, it can, it's sorry, if you have a constrained model, the model capacity is limited, but then your data fit is not so good, and the other way around, of course. If you have a very flexible model, it can fit anything, so the model capacity is large, but then your data, your data fit is good, but then you can fit everything. So, and of course, you can see this by, let's say, instead of maximizing, I want to be minimizing, so you just flip the signs. So you want to decrease both of these terms, and you want to decrease the model capacity. So you want to have simple models. So you don't want anything. You don't want a model which fits everything, but you also want to have a model that fits all your data. And again, I understand that this is not obvious how you go from this formula to this model capacity and data fit. So if you're interested, you have to we can talk more. But this is what happens in practice. So you want to maximize the marginal likelihood or minimize the negative marginal likelihood, log marginal likelihood. Now there are two problems. The problem is non-convex in the sense, meaning of course that you can have different minima. So it's not guaranteed that you end up in the global minima. So you may have to do several different. You start at different points and you optimization several times just to find the best solution. And it's so the fact that you have to balance the two things, the model capacity and the data fit, means that you are kind of to some extent guarding against, again, overfitting, which is not the perfect language, but against having a very flexible model. But it's not a complete guarantee. So it's always, in practice, if you do this, it's always a good idea to have some to do some cross validation, to have some test set, just so you can test your model. So this is one example again from this book. So you have, you do minimization, and it turns out that you have two solutions. As I said, it's non-convex, so you can end up with different solutions. So one of these solutions seems like a reasonable. This is the global minimum. So it seems like a good solution. So it balances the flexibility. It adds some noise. It looks like a good solution. But there is another solution which is more. It's not as good a fit for your data as this one, but it's more constrained. So you see how you can balance these two terms. And this is on this. At the end of the day, this is a better model, but this is also, in principle, this is a reasonable view of your data. It depends on, your how much noise you're willing to say you have. Maybe you have a much, that you have a lot of noise. Maybe this is a better a model. And in fact, there is a way to say, okay, to put at least some of these parameters you can just fix by hand and say, okay, I know that my model should have at least these kernels have this hyperparameter should be fixed, and then you can optimize for the other. So this is like some kind of mixed approach. Okay, so as I said, so this is the way to optimize these hyperparameters going to this marginal likelihood. At least this is the most commonly used way in practice. So there are other ways of doing it, but this is, and it seems to work pretty well. Okay, so as I said, or actually as Dan said, there are many different types of kernels. So we've been talking about the square exponential, which are the most widely used, but squared exponentials are a bit too smooth. You see, you always have these very smooth functions. So that may not be a reasonable expectation from your data. It obviously depends on what kind of data you have. So that is the second probably most widely used kernels are this matern. It's a family of kernels. It has this Bessel function, and you can actually, you have infinitely many of them. And the important parameter is this ni here, and actually ni 1/2, which is ni 1/2 is going to be just an pure exponent. So it's a very abrupt function. So you have this is one example function. You have this very fast changes. It still have a length scale. So this ni controls how smooth the function is, but you still have this length scale. Then there's this two, which you can see. If you write them, you see that there's basically a product of an exponential correlation, but multiplied by the polynomial. And of course, the higher the polynomial, or the smoother the function is. In the limit of infinitely high polynomial order, you get back the squared exponential. So you have this smoothness. So points which are close to each other are strongly correlated. And then you have, the good thing is that you have these in-between functions. So typically the most widely used are these 3/2 and 5/2, which are kind of not as smooth as square exponentials, but not as kind of crazy as pure exponential correlation. So you get this. So you still have the length scale, but you have a bit more of noise or jaggedness in not noise. You have a bit more variation on shorter length scales. Quadratic kernel, so which is it has a similar behavior. It has this, so it is, you can think of it as an integral over. I mean, this is where you can derive it. If it's an integral over different square exponentials, but with some kind of prior, and this how many of these you include is controlled by this parameter alpha. So you have this sum of different length scales. So if you have alpha goes to infinity, you just get squared exponentials, and you can how many different length scales you would mix is defined by alpha. So it's still short length scale is kind of smooth, but then you have different you can have different length scales mixed. So okay, and so okay, these are kernels which actually they vary around 0, which is you can of course always shift if your function is not changing, if it doesn't have a increase, it doesn't increase or decrease, you can always kind of shift it and make it centered around 0. But of course you can have function. Obviously you can have an increasing function or decreasing function or periodic function. So there are also kernels for that as well. So you can have a linear kernel, so you have this increasing trend. So these are examples of functions that you can get. You can have periodic kernels in case you have some kind of periodicity, or you have like something that repeats. So of course this is the squared exponential, as I said, and this is this rational quadratic. So it is these multi-scale variations. Now of course this is, even with those, it's still kind of a bit constrained. Now the good news is that you can actually combine all of these things. So a sum of two kernels is also a legitimate kernel, of course, because kernels have to have this physical meaning that it tells you what is the correlation between different points. It has to have this, it has to obey some mathematical constraints like semi-positive, the function has to be semi-positive, semi-positive, definite. But well, if you combine two legitimate kernels, the sum of two legitimate kernels is also a legitimate kernel. So for example, you can have a linear plus periodic, so you have some periodicity but on a trend. So instead of oscillating around 0, you can have actually oscillations around some trend, or you can have squared exponential plus periodic, so you have some periodicity but also you also have noise. Or you can have linear plus some kind of variations, or you can combine two different square exponentials depending on, you can have some short length scale variations, but there are also some long length scale variations. So you can have, now you have a much higher flexibility, and then the second good news is that the product of two legitimate kernels is also a legitimate kernel. So you don't have to worry about whether your kernels is an actual kernel. So you can multiply things like two linear functions, so you get quadratic function. You can have squared exponential multiplied by a periodic kernel, so you have something which is periodic for short length scales, but as you move away because of this squared exponential, actually the correlations decay. Or you can have a linear and square exponential, so you have some kind of increasing variation. Or you can have something, you can have a linear and periodic, so you have some kind of multiplied by periodics. You have increasing amplitude. And now, of course, if you can also do multiplication and sum, so you can starting with a few simple kernels, you can create this more and more complicated kernels by using just multiplication and sum. You can get some very complicated behaviors, but the good thing is that all of this is still, at least to some extent, interpretable. So you get stuff which is, you can interpret every piece of well, I mean, if you have a good idea of different different physical behavior from different subsystems or something, now you can attribute these the hyperparameters. You can, first of all, if you have some idea for your hyperparameters, what appropriate length scales, you can put it by hand, or you can constrain your optimization. Or if you don't have, then at the end, when you optimize your parameters, you can extract these hyperparameters and map them to some physically relevant variable. So that's pretty nice. Okay, so let me now try to go to the collab, and I'm using. So this is another version of the same collab. So it's created by Gilad and Dan. I don't have any really input. So this is GPy is the standard, one of the standard packages for Gaussian processes in Python. So so we import them. This is a function that helps us plot. So and now I think Dan went to that, so I don't have to explain all of these things. It takes some time to run that. Well, it takes a lot of time. Okay, yeah. So and as you see, even within the RBF or squared exponential family, you can have different behaviors depending on your parameters. So you can changing the length scale. You have this, and Dan explained this is a representation of the correlation matrix, and you see that along the diagonal points which are close to each other obviously are correlated, but then the correlations just decay as you move away from the diagonal. As you move away from the point, you know, it's not correlated with anything which is too far away. Now this is exponential. You see that this kind of correlation is even more constrained. You have this kind of sharp changes. Now this is this Matern kernel. It has this length scale, but it also has this kind of short length scale variations. And this is so you can see that this Matern 5 house is a bit smoother. So it's starting to look like a squared exponential, and it's kind of very quickly starts to look like squared exponential. So that's why this two are really the kind of typically used, because if your knee increases, if it's really large, then you should just use squared exponential. This is periodic. Now, of course, your correlations, you know, it kind of at each wavelength, of course, the correlation is now perfect because you get the original function. So this is cosine, and of course the points which are at half a level or half a wavelength are perfectly anti-correlated. So you see that the scale goes to -1. Brownian motion. So you have this white noise plus the previous position. So you have some drift. So this is linear. So you know you can combine all of these, and you can. So all of these are typically in any package for Gaussian processes are included. So you don't have to worry about them. Okay, maybe I should grab this. Okay, and now you can start combining them. Now, this is the last thing that I want to show. This is an example that I think Gilad coded. So you have this function, and you add some noise. So this is when you sample, you add some noise. So in principle, you should get something like this. Now, what we do is we sample 5 points and see what would be the GP optimization. So what kind of model the GP would produce. So let's run this, and you can, because you only have 5 points, you can get some quite interesting results. So, okay, so here, this looks like I mean, again, 5 points is not a lot, and really how your 5 points are distributed gives you, it has a huge impact on the result you get. Sometimes you get reasonable results, sometimes you get something which is not nearly as close to. Okay, so here you see, because you have the points are kind of not distributed well, you see this fit, which looks reasonable, but it's really quite a bit off. So you know, if you have a few points, then that's not good. That was, let's see if, okay, this is not so bad. This looks reasonable. Another one. This is also not bad, and you can see, you know, these are the parameters that you get at the end. So these are optimized parameters by maximizing the log likelihood, marginal likelihood. Okay, so this is good. Okay, I'm trying to get one example in which the length scale is going to be just very large, which sometimes happens. Let's see another one. No, this is still, and you can play with it. Okay. Okay, so and you know, you get different solutions. So, and that's you know, again, it really depends a lot on how your data points are distributed, and the more data points you have, of course, the better your fit is going to be. So that's but the good thing is that, you know, the GPy does that for you. You just have to say optimize and how many times to run the optimization, and then you get the result. So I think I'll stop here. So let me go back to my slides. I think this is the last one, and I think I'm over time. So if there are any questions,
see, any questions from the audience? I don't see any in the channel.
wow, everything is clear. That's amazing.
You can also ask questions if you had them of Dan. Okay, going once, going twice.
Okay. Yeah, okay, thank you. I apologize for taking some of Gilad's time. He said it's okay, so I hope he's not going to hate me. So thank you.
All right, so let's switch over to Gilad.
All right, it looks like my audio is up, and is my screen visible?
Looks good.
Okay, so I just want to briefly go back. I'll maximize the screen. I just want to briefly go back and again suggest anybody who's interested to look into our boot camp for machine learning for material science. You know, we teach everything hands-on with open source code, so it's a nice resource. So we've done all this GP content. So I'm now going to talk about active learning. How do you get machine learning to guide you on which experiment to do next or which data point to obtain next to improve your overall knowledge? So first off, the normal way of using machine learning is that, actually, can you see, is it possible to see my, my mouse?
Yes, it looks fine.
Okay, all right, awesome. Okay, so the first, so traditionally, what people do is they'll do an experiment by making a new material, measuring the material, and then they get all the data and they hand it off to an AI platform, which does analysis of the data. And then based on your understanding of the analysis that the AI does, you then decide what experiment to do next. Active learning allows you to, the AI doesn't just do the analysis, but it also tells you if you want to improve knowledge towards some objective, this is the next set of experiments you should perform.
Gilad, actually, a moment. We actually have a question from Jiyoung. So you're unmuted, so go ahead and ask your question.
Oh, I'm sorry. It's intended for the previous one.
Oh, he's still here. We're all on the line, so.
Oh, okay. I'll make it quick. So, as I know, the Gaussian process handles a little bit of a less amount of data compared to that of neural net models. So, what is the typical size of the data that the Gaussian process usually deal with?
Should I, Valentin, should I answer or do you want to answer?
I'll jump in. So,
okay.
You know, I think that there's sort of two sides to that. If you're talking about like the standard formulations that we've talked about, you're probably going to start to hit bottlenecks, you know, around a couple of thousand, you know, depending on what kind of compute resources you have, you may be able to stretch it to tens of thousands. But there are a variety of methods for, I mean, the big computational sink is creating the kernel matrix because it's a function of the sample size, right? So you have n sample points, you're going to be constructing this kernel that has n by n elements. But you can use various approximation methods such that you don't need to compute that entire dense kernel. One is that if you think back to the had for say the radial basis function, there were those large kind of blue regions. Those values were all effectively, if not exactly, then close to being equal to 0. So rather than computing the full matrix, you can just compute those elements that are non-zero, and you can use sparse methods to get some computational speedups. There are also alternative methods using an area of optimization, or loosely speaking optimization, called variational inference, where you are trying to find a distribution that closely approximates the one that you're interested in. And again, that's another approach for, rather than having to deal with the calculation of the entire kernel matrix, you can find a closely approximating distribution that, again, requires or removes the need to compute that entire kind of large chunk of data. So there are ways of extending it to larger sample sizes, but it is a good point that by and large, it often is constrained to smaller samples unless you kind of leverage some additional tools to get it to scale.
Okay, thank you. Sorry for the interruption.
Yeah, no, that's fine. Also, this package, GPy, that we use has built-in sparse methodologies. So you can, if you go to their website, you can look up different algorithms that you can call from GPy. Also, GPFlow, which is another package that's an expansion from GPy, but uses the TensorFlow framework, also has some really great sparse methodologies. Yeah, so it allows you to extend to thousands of data points.
All right, thanks.
Yeah, so once you have, even if you have small data or you have large data, often the question is, do you have the right data? Is the data that you have the data that you need to solve some objective that you have? So if you're trying to optimize a material for some property, maybe you have a lot of data, but it's not data that's useful in actually answering that question. So how can you use machine learning and specifically Gaussian processes to help guide you towards the right experiment to do next? And potentially, once you have that active learning step, the step which tells you what experiment to do next, you can actually have it run the experiments for you. If you can build a automated system, you can start building autonomous research systems. Okay, so the definition of active learning. Active learning is the machine learning aspect, the machine learning field where machine learning can actually request a new data point to either be labeled by a user or to collect specific data from an instrument. This fits under optimal experiment design. Let's see. All right, so an example is shown here where, let's say we have some apples and oranges, and we know that these are apples and we know that these are oranges, but we don't know what these fruits are. And we've plotted them on this axis of texture versus color. I just, some arbitrary two axes. So we know that these are apples and these are apples and these are oranges, and we want to figure out which of these fruits that we don't know what they are. We know their texture and color. That's why we have them plotted here in this diagram, but we don't know whether they're an apple or orange. Which one should we ask for a label for next? If we ask for this to be an apple, if we ask whether this is an apple or an orange, is that more informative than if we ask for this one to be an apple or an orange? And by I, what you might guess is that these points are likely to be apples and these points are likely to be oranges, but the the points somewhere in between are probably more informative as to where the best place to draw the line to differentiate between apples and oranges is. So it might pick, active learning might pick this point and say, label this point to identify if it's an apple and orange, and that will help us identify where that the barrier, the decision barrier should be. So there are two large subsections of active learning. One is unfortunately also called active learning. So this is a subclass of the larger class called active learning. This subclass is focused on identifying which data point is most useful to get global knowledge of your of the challenge that you're looking at. And the other subclass is often called Bayesian optimization, and this is where you want to figure out what's the data point which data points will allow you to more rapidly identify the maximum or minimum of some underlying function. So this might be used to identify the material that has a maximum hardness, while this technique will help you identify what's the underlying function that describes hardness as a function of say, composition or temperature or some other parameter of your materials. So again, active learning here, it might tell us that this fruit is the one that we might want to identify. In the case of a Gaussian process where we previously were looking, we just heard a lot about Gaussian processes. Here, let's say we have 5 data points, and these data points are generated from this underlying function, the dashed black line. The GP is guessing, has an estimate that the underlying function, the mean function, is this blue line, and it has uncertainty bounds indicated by this by the light blue regions. We have regions of uncertainty indicated by large blue regions and regions of low uncertainty close to our data points. So if we want to get maximal knowledge over this space, there are certain regions where we might want to query. So we might want data here where we have large uncertainty, here or here. For the Bayesian optimization aspect, we have the same data points, and our prediction, again, we have this estimate of what the function could look like, this blue line. And what we might say is we're interested in finding the maximum of this function, of the underlying function. And based on these points, we have a guess that probably the max is somewhere over here. So we would want to measure somewhere around here to figure out if we can identify the maximum. So to do this, to do active learning, we basically need 2 things. We need a function to represent our data as it comes in. And preferably, we want something that provides both an estimate and uncertainty in its prediction. And of course, here we can use our Gaussian processes, because this gives us a prediction of the estimate and uncertainty. We also need an acquisition function, which quantifies the utility or the desirability of performing the next, each of the next experiments. So as a simple example of for Bayesian optimization, we're going to start off with a methodology that focuses on pure exploitation. So in this case, again, we have 5 data points, and drawn from this underlying function, the dashed line, and the blue curve indicates where the GP is expecting expects the underlying function to be described by this mean curve here. And one thing we can do is we can use this curve and say that the maximum of this estimated curve is where we want to measure our next point. So in this case, the red dot here is the true maximum, and our GP says that it's expecting the maximum to be over here. So we're going to measure our data point over here. We measure this data point, and now the GP is predicting that the maximum is over here. So we then measure this point. This data point actually pins the Gaussian process estimate down to a non-optimal position. And so now we're converging on where the actual optimum is. So this is pure exploitation, where we're just using the data we already have to try to find where the maximum is. So in this case, the acquisition function is the mean of our GP, and what we're doing is we're trying to find the maximum of that mean. That is the next data point that we want. An alternative is something along the lines of active learning, where we want to, instead of exploit, we want to explore. So here, again, we're using the GP, where we have our 6 data points, and we have our GP's prediction of where the mean is and our uncertainty. And the acquisition function that we want is actually equal to the uncertainty, or to the variance of our GP. And what we want to do is we want to identify the points where we have the greatest variance or the greatest uncertainty in our GP. So in this case, you can see that the GP hasn't done a great fit to the data, and it has high uncertainty here. So we ask for a measurement here. We get that data point, and now the GP has a reasonably good fit, but it still has a region of high uncertainty, which is indicated by this red curve here. This is, again, the acquisition function, which is exactly the variance of our GP. So here we have high variance, so we're going to measure our data point here, and that then pins this point down. So you can see that now we've converged pretty well to our underlying function. And it can continue going on by identifying the points of greatest variance. So if we know what the actual maximum is, and we're doing Bayesian optimization, we're trying to find the maximum, and we already know what the maximum is, then we can use a technique called regret, or simple regret, or minimum regret, to sort of benchmark our algorithms to see how well does the Bayesian optimization algorithm work to find the maximum that we already know. So let's actually go to this other example here. So in this case, we see that the maximum is in this region here. We have this data point. So in this case, we know that the global max is 2.2. We have a data point over here, which is at -0.5. So we can compute what's the minimum regret, which is we take the maximum value of the set of points we have. In this case, we have only one data point, which is 0.5, and we take the max minus the true max minus the estimated max, and we get a value here, 2.7. So this is the minimum regret. So in the case of where we have 1, 2, 3, 4 data points, here are the y values for those 4 data points. We take the maximum value of these, which in this case is 2.2. The true max is 2.2. So the minimum regret is 2.2 minus 2.2, which is 0. So this is one way to measure how quickly you find the optimal. And we'll see a case of how to use this in the co-laboratory. If instead of trying to figure out where the maximum is, we're trying to figure out how well our GP is describing the full function in an active learning task, one way we can measure, again, if we know the true function, one way we can measure performance of our algorithm is we look at the residuals between our true function, the dashed line here, f dash, and our estimate, which is the blue line, the blue curve. And we can use root mean squared error to compute how well the two agree. I see, okay. And also, if we don't know the correct answer, we can actually use convergence. So in this case, we're interested in finding the maximum of this function, and we don't know where that we don't actually know what it is, so we can't use minimum regret. So instead what we can do is we can see if our algorithm eventually converges to some response, to some answer. So in this case, we're doing sampling of this function, and at some point our y is converging to 2.2, or our x is converging to some location, in this case 130, 130. At this point, we can shift our mode of optimization. Okay, so, and this is a great example here of where we can balance both exploitation and exploration. So we saw that if we maximize the mean of the GP, this helps us find the maximum locally of the data. And if we maximize the variance, then this helps us get a better idea of what the total function looks like. So if we balance these two, this can actually help us do optimization over a large, more complex function. So in this case, we have a balancing between we're adding the mean plus some weight times the variance. And an example of this operation is shown here, where in the first case, here we have beta equals 1, so we're doing equal balancing between exploitation and exploration. We have our 1, 2, 3 data points, and this is where our true max is. So initially, we're sampling where the variance is very high. So actually, a good way to think about this acquisition function is, so it's the sum of the mean and the variance. And what you can see here is we take the mean value here plus this distance, which is the length of our, so this is our variance, and this gives us our acquisition function. So for any point along this axis, we can just take the mean plus the variance. So actually, it's basically describing this curve here, which is the upper bound of our GP visualization. So in this case, it first wants to maximize this acquisition function. Over here, it collects this data point, pinning the curve at the edge. Now we have greater uncertainty in this region, which gets us to take a sample in this region. We get this data point, and again, we're looking at the upper bound of this curve. So this is called Bayesian optimization upper confidence bounds, and due to the fact that we're looking at the upper bound of the confidence interval of this of our GP. So now the upper bound here is indicated by the purple line again. So we collect this data point, and again we have another value, and eventually the upper confidence bound converges to the maximum. Because this is again the highest point in our acquisition function. Another example which lets us balance exploitation and exploration is a technique called Thompson sampling. What we do is we use a technique where we basically sample our GP. So here again we have our data points. We have no data points in this region. So our estimate for our GP, our mean estimate is here, the blue line, and again we have our uncertainty. So what we do is we just sample from this space. So this red curve is one function that's sampled from this space. We just take the maximum of that function, and so then we pin that point. So now we identify our the next point to measure from this function. We have that data point. Then we sample again, and we then take the maximum from that sample. We sample again, we take the maximum, we keep iterating until eventually we converge towards finding where the maximum is. There are a bunch of other algorithms for identifying, for doing Bayesian optimization or active learning. In this case, this one's called probability of improvement, and it focuses on identifying the max point that you've already measured, and then summing the probability of the curve at every location on X, and using that to identify the next point to measure. So in this case, we have a larger probability, a larger portion of our Gaussian is above the curve here, so we're more likely to measure on the left side here. However, this technique doesn't care how big the improvement is. It's just looking for the highest probability of getting an improvement. So we can use another technique, which is expected improvement, which takes into account the likelihood of what the expected value we would get at each location. All right, so let's go to the, do we have any questions?
I haven't seen any question yet on the question dashboard. So if you have any question, please feel free to put it in or raise your hand or anything. I should be able to see it.
Okay, so I am now starting my collab using the link that you guys all have. Yeah. So while this is loading, we have used a lot of different active learning techniques coupled with Bayesian methods similar to GPs to do optimization of different experiments. And we have actually built it into fully autonomous systems in chemistry and material science. And we're also working on genetics, an autonomous system in genetics, where the GP and the active learning decide what experiment to do next that maximize that help us towards some objective that we define. And it then does the experiment for us, collects the data, and goes on to the next set of experiments. Okay, so that part's done. We've discussed all of this, or Dan and Valentin have discussed all these aspects. So this allows us to plot the GP predictions. We looked at different types of kernels. Okay, so here again, we have some function.
So Gilad, sorry to interrupt. We do have one question from Christoph. Christoph, I just unmuted you. Do you mind just speaking up?
Oh, hi, thank you. Thank you for this wonderful tutorial and workshop. Sorry we can't attend in person. So my question is regarding a little bit discussing the statistical regression methods, which kind of like minimize the number of measurements required to achieve a particular model quality. I know when you talked about incorporating this into larger experiments, sometimes the goals might be to minimize maybe the experiment duration or the material usage. So how and where would you add something like an adaptive cost function to allow your autonomous algorithm to balance new information gain against such experimental costs?
Yeah, so we don't have that built into this tutorial. I can provide a few links after the tutorial, you know, that provide some overview about different methods for this sort of constraints, the constraint programming aspect of incorporating costs into your optimization. Yeah.
Oh, thank you.
Yeah. Yeah, so initially we're going to start off with this function, the sine plus a linear function, which we'd like to optimize. Valentin showed this code already, where we have some underlying function and we're sampling it. In this case, we're sampling 5 data points, and we're fitting a Gaussian process to get the mean and variance of the estimates of the GP. And here we have a set of code for actually sampling our GP. Each of these colored curves indicates a possible sample. Okay, so in this this code sort of factorizes the rest of the code, allows us to do all the GP analysis in one function, and this function allows us to plot everything that we need. So here, in this first set of code, we're going to do Bayesian optimization specifically for optimizing the mean. So here we're choosing the number of samples we want. This is how many iterations we're going to allow the Bayesian optimization to go through. We're going to evaluate our methodology using minimum regret. So for this, we need our correct max or true max. And okay, so here we're taking our first samples, our first 5 samples of our data, computing what their values are. Then we have, this is the actual Bayesian optimization for loop, where we have our 5 data points. We then use our GP to compute the mean and covariance for our fit. Our alpha function, or our acquisition function, is based on the mean of the GP. And we then, we want to find the maximum of that mean. So we can use the argmax function. And then we plot the results. Once we've identified the next point to measure, which is this next sample here, the next sample index, which is computed from this argmax, we then add that to our data set and iterate again. And so if we run this code, what you can see is that here we have our initial data points. You see that, as Valentin indicated, the GP has converged to not the best answer, one where we have a very long length scale. So we collect a data point and we keep iterating where we believe the maximum is, indicated by the maximum of the mean. And oof, everything's happening at the same time. Yeah. As we collect more data, the length scale converges to a better answer. Although I think here, yeah, so we again have this iteration where we get a bad convergence, but let's see, yeah. Actually, it ends with a bad convergence, but you can keep playing around with this to see what kinds of responses you get. In this case, what you see is that it's converged to an incorrect optimal because it hasn't done any measurements over here, so it has no information in between these data points. So it's using pure exploitation. It's just using prior data to try to find a max, and since it has no data here, it can't do that optimization. So the next set of code, here is our code for computing minimum regret, and you can see that the minimum regret converges to 0.6 rather than 0, indicating that we did not find the best answer. We can then look also at convergence measures. Oh, this is for looking at the root mean squared error. How well did we find the true function? These are building in all these parameter functions. So next we have some data where what we're doing is we're looking at doing pure exploration. So instead of looking at the mean, we're looking at the variance of our GP, again in 10 iterations. And here we have one data point. We have high uncertainty in this region, so we get a data point here, and we continue to iterate until we get a convergence to a decent prediction of our algorithm, of our underlying function. And finally, we have a mixture of exploration and exploitation using the upper confidence bound methodology that we discussed. And actually here we're using in the slides we used a beta of 1. Here we're using a specific function for beta, which unfortunately I forgot to reference. I will also include that in the chat once I'm done. And so this balances exploration and exploitation. And what you see is very rapidly it finds the maximum. So here we have, oh, unfortunately it already knows where the maximum is. Let's try another. Okay. Yeah, so here we have some data points away from the max. And very quickly it's starting to converge. So it's starting to sample close to the maximum, and it converges within, I don't know how many steps that is, maybe 3 steps, 4 steps, it finds the maximum. So this method is a very well used, very well understood method. And here again, we can plot the metrics of our algorithm and see that minimum regret falls to 0 very rapidly. And we can use Thompson sampling, which is the other algorithm that we talked about, where rather than using a predefined acquisition function, we just sample our Gaussian process and use the maximum of the sample. So here we have a GP and we sample it. This red curve is the sample, and we take the maximum of that sample. And as we go forward, we see that here the maximum is now at the correct location. So we've converged to a good answer. And there is some other code here. In how to use, rather than writing your own acquisition function, if you'd like to use one that's built in, GPy has a sister package called GPy-opt, which has different acquisition functions. In this case, expected improvement, lower confidence bound, and maximum probable. Actually, I'm not sure what this one is. I can't remember what that one stands for. So what this code does is it just shows you how to combine, and something failed. Oh, because I didn't run this code. How to combine Gaussian GPy with the optimization toolkit, where first we use the GPy to generate our mean covariance and our model. We then hand that off to the acquisition toolbox, and we can use it then to define where the next sample should be. And one thing that might be interesting to do is to look at, if we're trying to benchmark different algorithms for finding an optimal, we might want to see how it performs over multiple iterations. And this code will generate many curves for minimum regrets. Let's see. Yeah, so one way to, actually, let's go down to, this will show multiple runs of the upper confidence bound. I should have lowered the number of, okay, there we go. Yeah, and what you can see is that this method finds the optimal over a different number of iterations based on where we start off. And hopefully this code is useful for anybody who's interested in doing this kind of analysis. So that's all I have. Are there any questions for any of us?
I don't see any new questions, Gilad, so let's see. If it's easier, if you have any question, please also, you can try raising your hand. I should be able to see it too.
Dan or Valentin, do either of you have anything else interesting? I can actually show some slides of this type of code in action. So here we're using active learning, where the goal is to find the maximal, to maximize knowledge of the underlying function. So here we have what's called a combinatorial library, where each sample on this wafer is slightly different in how it's made in its composition, so that each point on this wafer is indicated by a point in this composition diagram here. And our active learning algorithm, what it's trying to do is it's trying to find which points are most interesting, are most informative towards finding out, towards computing the phase diagram. Here we're trying to figure out where the correct phase boundaries are. And what you can see is that at each case, the red point is the sample that the active learning is requesting to measure next on the wafer. It's then, that request is then sent to an X-ray diffraction system, which measures the point, updates our prediction, and we get a convergence towards the correct phase boundaries. We can extend this in from composition to, from just composition space to composition and temperature, where we're again looking at phase boundaries. And we can also use a similar technique of balancing exploration and exploitation to find a material with the highest material property, in this case, remnant magnetization. So in this case, we want to maximize remnant magnetization, but we also want to explore material structure using the phase diagram. And we can show that by balancing exploration and exploitation, you get more rapid convergence. And again, here we're using the minimum regret than other techniques. And yeah, so that's all the slides I have.
So we do have another question from Christoph.
So my question just had to pertain to one of the previous slides from the collab worksheet, in which case the algorithm did not converge to the maximum. So what sorts of adaptations would you do to the code to allow it to maybe sample randomly, or like how would you make sure that it actually converges to the global maximum?
Yeah, so random sampling is definitely one way of doing exploration. It's not a informed way of doing exploration. By balancing in there are certain techniques that focus on exploration. By balancing those in, you will generally find, so exploitation methods will find the local maximum close to the points that you've already identified. There are exploration methods similar to, let's see, where was that? Yeah, so maximizing the variance is another method that that allows you to do exploration. And then there are, oh, it's down here. So balancing a mixture of maximizing mean and variance using a technique like upper confidence bound or doing Thompson sampling. Both of those techniques allow you to ensure that over time, even if you are converging towards some local maximum, after a while you will then snap over towards areas where you haven't explored very much. And eventually you'll start finding eventually you'll find the global maximum. Yeah, so here's again is the example where we're using exploitation, which is maximizing the mean, and exploration where we're maximizing the variance. And we have some balancing function here. This is iteration dependent, so you can have it so that it's initially doing exploitation and eventually once you find a local maximum, it will then start to explore, or you can have the opposite, which is you try to get a sense of the general function before you try to converge towards a mean, towards a maximum.
Ah, thank you.
Okay, at this moment, I don't see more questions on the dashboard. If there are no more questions, I'd like to propose that we take a, say, 4-minute break and have Jonathan up at 3 p.m. sharp.
Sounds good.
Okay. Okay. Bailey, I see you are asking a question. Let me unmute you. I believe that most of the presenters are still online. If you don't mind just asking it out loud. Oh, you are asking about the slides availability. So this webinar is recorded, and we will have the YouTube recording links out to all the meeting attendees. And also, if you follow us GDS APS on YouTube, we should be posting everything on YouTube channels. In terms of the slide availability, that would be up to the presenters to see whether each of the presenters are willing to share their slides, and if they are, we will be distributing the links as well. Okay. And Jonathan, you are up next. Let me just make you presenter, and let me go ahead and try your audio and video first. Okay.
Okay, can you hear me?
Yep, I can hear you okay.
And let me try to turn my video on as well. Can you see me?
Yep,
Great.
that's perfect. Let's see. And at the same time, Jonathan, if you don't mind posting out the collab link to the chat box, that would be great.
Yes, sure.
So I just posted the Google Colab link to the entire audience. At this moment, if you cannot access it or if you couldn't find the link, please put it in the questions box and I'll be able to address it. So we are at 3, and Jonathan, I will hand it over to you.
Okay, great. Thank you so much. I'm also going to keep the link at the top here. So anyone watching can just go to this link and access the Google Colab notebook. And I'd encourage you to try to open up this Colab notebook and follow along. I'll basically just be going through this document. And I have some slides in here as well. Okay, so thank you to the GDS for organizing this great webinar on Gaussian processes and active learning, and also to the other panelists for the great talks so far. I'm basically going to be drilling down into a particular application of active learning applied to the domain of computational material science and atomistic simulation. And we're basically going to be working with this program FLARE, Fast Learning of Atomistic Rare Events, which allows you to use Gaussian process regression to train machine learning models of force fields for molecular dynamics. So if you don't have much of a background in MD, I'll just briefly review what molecular dynamics is and why it's useful. So basically the idea is we would like to be able to simulate pretty much any material at the atomistic scale. And to do that with MD, what we do is we take a collection of atoms and we put them in a box. Okay, usually this box is periodic so that we can look at periodic extended systems. And in a molecular dynamics simulation, basically we repeat these 2 key steps. So we have some energy model that allows us to compute forces on all of the atoms at a particular point in time. And once we have those forces, because we're treating the nuclei of the atoms as kind of classical objects, because they're much, much heavier than the electrons, we can use those forces to update their positions, essentially just using Newton's second law. And then you repeat these steps over and over again. So you compute the forces, use those forces to update the positions, and you do that in a typical, production molecular dynamics run. You can do that millions of times to look at nanosecond timescales. And often, the system sizes can be quite large, so tens of thousands or even millions of atoms that you're interested in simulating. So the method is quite general. In principle, you can look at all sorts of different materials, so organic systems, ionic liquids, metals, surfaces, and so on. Really what it comes down to is getting a good model for forces between atoms in the system. So, and what do I mean by a good model of forces? Basically, what you want at the end of the day is a model that's in good agreement with quantum mechanics, essentially. So if you were to, take your system and solve the Schrodinger equation exactly and look at the forces that come out of that solution, your force field is good if it's sort of in good agreement with that ground truth. The problem is that, solving the Schrodinger equation when you have lots of electrons in the system is incredibly expensive. Okay, you can't do it exactly. You have to use some kind of approximate scheme. Usually, density functional theory is the workhorse that gets used, and even that is quite expensive. So it scales typically cubically with the size of the system, and you can only scale it up usually to a couple hundred atoms tops. And so what's needed is some way of getting the accuracy of quantum mechanics, or at least approximate methods like DFT, but making it much, much cheaper. So ideally, you would have a model that scales linear with the size of the system, so that you can really sort of scale it up to thousands or even millions of atoms without losing accuracy. And this is sort of where machine learning has come into play in the last decade or so, and has become quite a powerful tool for basically bridging this gap and allowing you to get both speed and accuracy. And the idea essentially is that, if you have a bunch of quantum mechanical data, so forces on atoms for sort of bite-sized systems that DFT can handle, you can use those forces and energies to parameterize a machine learning model, which can then be used to run longer simulations and bigger simulations, and allow you to potentially tackle materials that would otherwise be impossible to handle with with brute force ab initio molecular dynamics. So this is kind of the application space that I'll be discussing for the next hour or so. And what I'm going to be talking about is a tool that we've been developing at Harvard in the Material Intelligence Research Group, led by Professor Boris Kozinsky. And it's a method that we're calling FLARE, which stands for Fast Learning of Atomistic Rare Events. And really at the heart of this method is Gaussian process regression. We want a force field that not just gives us, forces on atoms, but also uncertainties on those forces, so that we can tell how close are we to our reference data, to our quantum mechanical reference data. So this diagram here sort of gives you a quick overview of how the code works. Essentially, you start with pretty much nothing in your training set, and you make some initial call to DFT using some model system that's close to what you want to simulate. And you run a DFT calculation, compute quantum mechanical forces on the atoms, and use those forces to train an initial Gaussian process model. Okay, and then at that point, you can have the model predict the next frame, the forces on the next frame in the simulation. And if the errors are unacceptably high at that point, you're going to stay in this right loop, okay, where you call DFT and retrain the model. Okay, and this is quite an expensive loop because these DFT calculations can often take hours just to do a single point calculation. But at a certain point, once the error on your GP has gone below some acceptable threshold, you can sort of enter this left loop where you let the model completely take over the simulation. So basically, the model will predict forces on all the atoms, and then using those forces, you can update the positions. And if you have enough data, you can sort of stay in this left loop, and the simulation is significantly accelerated. And then, once this training process is complete, you can take that force field that you've trained and use, a program like LAMMPS to do some pretty interesting larger scale simulations. So this particular example, which I'll discuss sort of later in the presentation, is on silver iodide, where we could scale it up to about 10,000 atoms and do about a nanosecond of simulation time, which is about 1 million time steps, to study things like phase transitions and ion diffusivity in the material. So that's a broad overview of what I'll be discussing. And now let's sort of move on to the hands-on portion of the notebook. Again, this link at the top will take you to exactly the notebook that I'm working with. You'll have to go into playground mode if you want to run things. So the first thing we'll do is install the program. So here we're just going to run this. And basically, we're going to install the code through pip. So it should do everything automatically, and also install all the dependencies of the code. So things like ASE will be installed, and a just-in-time compiler numba, which sort of accelerates some of the rote portions of the code that involve lots of for loops. And this will take about a minute. So if you haven't already, go ahead and try to run this block of code and install the software. Okay, so it just finished on my screen. Probably it'll be finishing on yours in a few seconds. And the test to see that everything is installed correctly is to import the FLARE package here. So I'm going to run this line of code and make sure that everything works okay. Okay. And as long as that ran, you should be good to go. The tutorial should work just fine. And the next block of code, I'm just going to go ahead and import all of the packages that we'll use for the rest of this presentation. So things like matplotlib, numpy, ASE, and so on. So we can run that. Okay. So I've broken this notebook into two parts. The first part is on training a Gaussian process force field on a fixed set of ab initio molecular dynamics data. And then the second part is going to be on actually doing a fully on-the-fly active learning protocol learning a force field automatically using a Gaussian process model. So let's dive into this first part. I've put some data on an online repository, Zenodo, which you can install just by running this block of code. So if you Shift-Enter, we'll also unzip the files. Okay, and this should take a few seconds. And you'll now see, if you click on the files part of the notebook, you should find a folder called AGI data. AGI stands for silver iodide. And I'll just open up a movie that I put in there to show you what kind of data we're dealing with. This will just take a couple of seconds to download. Okay, let's pull that up. So basically, this is the reference data that we are dealing with. It's a fairly small simulation cell because we compute a DFT at every single time step. So it's quite expensive. And here I'll hit play and show you kind of what's going on in this simple ab initio molecular dynamics simulation. And I'll say this is sort of a typical size system that you tackle with AIMD. It's usually quite small because it's painfully expensive to do this kind of simulation. The red atoms here are the silvers, the blues are the iodines. Might be the other way around, but in any case, what we're going to do essentially is use data from this AIMD simulation, so all of the forces that came out of it, to train a Gaussian process model. And I'll kind of walk you through what the steps are that you need to go through in order to do that. Okay, so let's go back to the notebook here. I'll close this, and I'll also put the URL at the top. Okay. And let's just run this block of code, which is going to take the forces and the positions from that AIMD simulation and store them as NumPy arrays. Okay, so now what we're going to do is train a Gaussian process force field. And before we actually run the code, I'm going to go through a few slides and explain some of the theory behind these Gaussian process force fields, how the flare code trains them. So essentially what we're doing is trying to learn a model of what's called the Born-Oppenheimer potential energy surface. That's kind of a fancy term that just stands for, what is the energy of the system of atoms as a function of their coordinates. So in full generality, this function is pretty high dimensional and it's quite complex. So if you have n atoms in your system, it's a function of 3n variables. So that's kind of a hard problem, even with sophisticated machine learning models. But what we can do to make it quite a bit easier is make a few simplifying assumptions about the structure of this potential energy surface. So the simplifying assumption that we make is that it's only small clusters of atoms that are going to contribute to this energy. So if you look at this diagram on the right here, if we pick out a particular atom in the material, atom I, and we just look at a small local neighborhood around that atom, the assumption is that it's just these clusters of 2 and 3 atoms that contribute to the energy. So basically, we're building a 2 and 3 body force field, and that dramatically simplifies the regression task. So instead of learning this high-dimensional potential energy surface, which takes in all of the coordinates at once, we now just have to deal with these local atomic environments. And the regression task is to learn these functions. So what is the energy that's assigned to each pair of atoms? And that's a function of the chemical species of the atoms and the distance between them. And same for the 3-body contribution. So we look at triplets of atoms inside of a local atomic environment, and we ask, what is the energy contribution that triplet of atoms makes to the total energy, which is also a function of the chemical species of the atoms inside the triplet and the 3 distances that make up that triplet. And basically, we're not going to make any assumption about what the form is of these 2 and 3 body contributions. We're going to let the Gaussian process kind of learn the best function directly from our ab initio reference data. So this makes the force field quite low dimensional and also has a lot of other nice properties. If we make this assumption, it allows us to, once the force field is trained, to do really big simulations, because at the end of the day, we only have to deal with these 2 and 3 body contributions, which is a big benefit for doing fairly large scale molecular dynamics simulations. So that's the force field we're trying to learn. And in the last few presentations, we've heard a lot about the kernels of the Gaussian process model and how that plays kind of a critical role in the performance of the model. So this is the kernel that we use in this application. And in this slide, I'm showing you basically the 2-body kernel that we use, and the 3-body kernel is quite similar. So, at the top of the slide here, I've labeled it covariant. And the reason that we want our kernel to be covariant is because if you take your system of atoms and you rotate them in some way, the forces that the model predicts should rotate in precisely the same way. So we want to make this force field that we're learning be exactly rotationally covariant. And the way that we accomplish that is by building it directly into the kernel function that we choose. So at the bottom here, I'm showing you the 2-body energy kernel. So essentially what we're doing is making a comparison of the bond lengths of these 2 pairs of atoms, putting that through a smooth exponential kernel. And there's some species dependence. So if the pairs of atoms are not of the same type, so if the chemical species don't agree, then the kernel goes to 0. And we also apply a smooth cutoff function so that, as atoms start to enter the cutoff sphere and cross that boundary, there's smooth dependence of the energy function. And to make the kernel covariant, what you do is you take essentially derivatives of this energy kernel. So we would take derivatives of the Cartesian coordinates of the atoms, and that gives us a fully covariant model of forces inside of the material. So this is the kernel function we'll be using. And finally, once we've defined a good kernel, we can use that to build a Gaussian process model. So this is what our GP force fields do, essentially. So again, we're learning these 2 and 3 body contributions to the energy from DFT data. And the GP is going to give us estimates of the force components on all of the atoms in the system. And crucially, and really conveniently, it's also going to give us uncertainties on all of those force components. So we can tell when the model is sort of being applied to atomic environments that it hasn't seen before. So again, just a quick review of what this looks like. And again, we've seen this in the last couple of talks. So to make a prediction on forces, we have the standard kind of GP mean prediction, where we perform a weighted sum of kernels over the training points. And our uncertainty estimate breaks down into 2 pieces. So there's this noise component, which is coming from fundamental variability in the data that the model isn't able to capture. And there's this really important, what I'll call epistemic component, which is telling you, how far away is your current test point from all of the points in the training set. And for us, the epistemic uncertainty is going to tell us when we need to make a new call to DFT to update our Gaussian process model. And on the right here, this is sort of the classic picture of a one-dimensional Gaussian process. So right on your training points, the uncertainties essentially go to 0. The model becomes very confident in making predictions. And as you start to stray from those training points, the uncertainty goes up. And you can imagine when we're actually doing this for a big complex material, it's a more complicated regression problem, but the essential idea is the same. If you move away from the training manifold, roughly speaking, the Gaussian processes uncertainties increase, and that allows you to basically make a judgment about updating the model with new data. Okay, so that's it for the theory section. Now we're going to walk through training a model on that ab initio molecular dynamics simulation that I just showed you. So first thing, let's create a Gaussian process object using the Flare code that we installed at the top of the notebook. So what that entails is basically just setting the kernel. So we're going to use a 2+3 body multi-component kernel. And we're also going to define the gradient of the kernel so that we can do hyperparameter optimization. We need to choose basically an initial set of hyperparameters, and I'll show you what the meaning of each of these numbers are a little bit later. But the initial choice can be bad. We're going to optimize the hyperparameters in a couple of minutes. The other really important thing you have to set when you're defining a Gaussian process force field is the cutoff of the model. So if I go back up to this picture here, the 2-body cutoff usually is larger because it's quite cheaper to evaluate this 2-body kernel, and the 3-body cutoff is usually a little bit shorter. But basically, we're defining the radius of these 2 spheres in angstrom. Okay, so we set our cutoffs, and we set the number of hyperparameter optimization steps that we want to take when we optimize the hyperparameters. Okay, and then this line here is just going to initialize the Gaussian process model. Okay, so I'll run that. And now what we're going to do is update the training set of the model. We'll basically take 2 snapshots from that ab initio molecular dynamics simulation. We'll take the positions and the forces and use them to create a training structure. And then we'll put that training structure into the Gaussian process training set, and then update the covariance matrix. Okay, so this will take probably about 10 or so seconds. We'll let that run. And now we basically have a GP model, and we can compute the marginal likelihood, which is going to tell us how good or bad our hyperparameter choice was. And you can see the marginal likelihood is really negative, which is not a good sign. It suggests that we need to do a little bit of work to get more reasonable hyperparameters. So, you know, let's sort of dig in a little bit deeper on how we choose these hyperparameters. So remember, when we initialized the GP, we had these 5 kind of mysterious numbers that we needed to choose. So what those numbers are, they correspond to signal variances. So if we go back up to our kernel, it's this sigma hyperparameter that shows up in the kernel, and length scales. So in the squared exponential kernel, you see this L hyperparameter. Basically, this is defining the characteristic length scale of the force field, and it's in units of angstrom. And then finally, the last hyperparameter is the noise hyperparameter. So that's telling us, you know, once the model is completely trained, what's the typical error level of the force field? And that's going to be in units of EV per angstrom. So, you know, how do we go about selecting reasonable values? We can, you know, make a good choice based on some physical intuition. So you can ask, you know, what's actually a plausible length scale for a force field? In other words, if you look at your system of atoms, what's the characteristic distance between atoms? And usually that's, you know, around angstrom kind of length scale. And so it'd be reasonable to pick roughly 1 angstrom for the length scale. Similarly, you know, a good force field often has typical errors in the range of 50 to 200 MeV per angstrom. So that's not a bad choice for the noise hyperparameter. So, you know, you can play around with setting the hyperparameters of the GP. You know, if you play around a bunch, you can see, you know, these are reasonable values to choose, a length scale of about 1 angstrom, and a noise hyperparameter of about 200 MeV per angstrom. If you do that, you'll get a likelihood that's now positive. But you don't really want to play this game for too long. It becomes tedious to optimize hyperparameters in this manual way. And so what we can do is try to rigorously maximize the log marginal likelihood of the GP. So basically, we can compute the likelihood of the model with the given hyperparameters and also the gradient of the likelihood. And we can use that gradient information to take steps in the direction of the maximum marginal likelihood. So I'll run this code block, and this is going to initialize the hyperparameter optimization routine. And you'll see it kind of takes time. it's going to print the progress of each step, so we can see what are the current hyperparameters, what's the current likelihood, and what is the gradient. And basically, this is running just standard BFGS gradient ascent to try to maximize the marginal likelihood. It takes some bad initial steps here. You can see -600, -400, but eventually we're going to start hitting positive values. And you would let this run for a while until you've sort of converged to a value of the likelihood that that's good enough. You can see now we're sort of in the positive territory, so, and it'll keep going up for a while. I won't bore you and wait until convergence, so I'll just stop this this block of code if I can. Okay, it took a little bit of effort to stop it, but basically, if you keep running it, you'll land on this set of hyperparameters, which, if we compute the likelihood, you can see it's now quite positive, a lot better than our initial guess. So this is sort of a really important step to take to make sure that you're getting the best sort of bang for your buck with your GP model. You really want the hyperparameters to be as good as possible, both to get good performance of the model, but also to get good uncertainty estimates. It turns out to be very critical to go through this step. Okay, so now that we have good hyperparameters and we have some training data, we can do a few things with the GP. And so I'll go through a couple of brief exercises showing you some typical steps that you would take to train a good Gaussian process model on DFT force data. So one really important thing to compute almost always if you're training a machine learning model is the learning curve. So basically what that is model performance as a function of the size of the training set. And we're going to do that in a very sort of abbreviated fashion, but it should give you the idea. So essentially we'll choose just a single training snapshot. So frame 500 of our AIMD simulation, and a single validation snapshot. So what we'll do is add atomic environments one by one to the training set. And every time we make an update, we will look at the error on our validation snapshot and see sort of how it behaves as we add more and more data to the model. So let's run that block of code. And now this block will compute the learning curve for us. So I'll start running it. It takes a little bit of time. So the for loop here is going through the atoms in the training structure. It's updating the training set of the GP and resetting the covariance matrix. And then once the GP has been updated, we predict the forces on the validation structure. Okay, and we compute the mean absolute error. And here, we're printing it as it makes each update. And you can see it going down, which is a good sign. This is in EV per angstrom. Okay, so we'll let that finish. Okay, and let's plot the learning curve. So it's a bit choppy because we're using such a small validation set, but it's giving you the behavior that you typically see with a learning curve. So as you add more and more training environments, the MAE initially goes down quite rapidly, and then you sort of slow down as you add more data and converge to a particular error level. The second plot that I'm showing you is the prediction time. So how long does it actually take in seconds to evaluate the forces on all the atoms in the validation structure? And this is the typical behavior that you see with a GP. It's dependent on the size of the training set. So as you add more and more data, the model becomes slower and slower. And this is something that you sort of have to contend with if you are interested in applications that sort of need to be really, really fast. And molecular dynamics is kind of an example of this. So there are tricks you can play to take the Gaussian process model and map it onto something that's independent of the training set. I won't go through it in detail in this presentation, but there is a way to sort of accelerate the GP so that it's suitable for really intense MD simulations. So that's sort of the first half of this notebook. I wanted to show you an example of our application of basically the same workflow of taking an AIMD simulation, using the forces from that simulation to train a GP model, and then doing much larger scale MD simulations. This is work that was done recently by David Lim. And the ChemArchive number is here if you're interested in reading about it. But basically, what we did here was we took an AIMD simulation of a bunch of palladium atoms on a silver surface. And we wanted to know how this palladium island restructures on the silver surface at different temperatures. And it's something that experimentalists have been able to look at a little bit, but hasn't really been well understood at the atomistic scale. So what we did was we trained a Gaussian process model on a fairly modest amount of training data. It only took about half a day to train the model in the end. And we compared it to some of the off-the-shelf force fields that are available for this type of system. You can see the red dots here are the errors of this EAM potential. Blue dots are the errors of the GP model relative to DFT. So we want the agreement to be as good as possible in order to get the most realistic simulation. And you can see sort of this is what machine learning allows you to do. You can take a system where you don't really have an existing force field that works and get really good forces that are in good agreement with density functional theory. And then you can use the resulting model to do pretty big simulations. So this is sort of an example of a fairly long simulation of about 2 microseconds. And you can look at what happens to this island of palladium atoms as the simulation unfolds. And what we saw was silver starts to hop on top of this island. And after about a microsecond or two, these vacancy pits start to form. So the formerly pristine silver surface starts to have these massive rips in them. And that's what we saw in the simulation, and it was in quite good agreement with STM images. So there's this nice sort of unity between simulation and experiment, and it's really sort of fueled by machine learning and getting good force fields that are in agreement with quantum mechanics. Okay, so that's the first half of this notebook. I'll maybe pause for a minute or so to see if there are any questions.
Okay, so you have
Yeah.
two questions, maybe more. So one is from Thomas Susi, asking, what are the strengths and weaknesses of GP force fields compared to neural network force fields?
Yeah, that's a great question. So basically, in the literature right now, GPs and neural networks are kind of the leading approaches that are taken. What GPs afford you are good uncertainty estimates, and that can be difficult to get with a neural network model, especially if it's a really deep model. One of the big open problems in machine learning right now is how do you get uncertainties that are well calibrated with super deep models. And there are a range of approximate approaches that you can take. So you can try to define a Bayesian neural network and do approximate sampling of the posterior, but often that's quite expensive to do. So what the GP gives you is basically this nice analytic expression for the predictive posterior of the model, and it allows you to compute these uncertainties in a fairly efficient way. So for us, that opens up this interesting on-the-fly loop where you can sort of automate the process of designing your training set. With a neural network model, it's a little bit tricky to do that.
Let's see.
Hey, Thomas, I think you are unmuted. If you don't mind, can you let us know whether you're okay with the answer?
Yeah, thank you. I was a little bit confused with the terminology in the beginning. So at least in Europe, we call these Gaussian approximation potentials, GAPs. So I've never seen this Gaussian process terminology before, so it took me a while to realize that we're talking about the same thing.
Yeah, so it's a little bit different from the GAP framework in the kernel choice that we make. So Gaussian approximation potentials use the SOAP kernel. Let me go back up to our definitions here.
That's not exactly true. I mean, there are various kernel choices, and they all are kind of discussed in the context of Gaussian approximation potentials. I'm not an expert on that literature, but I've seen multiple different kernels being used there.
Yeah, so basically the idea is the machine learning model that we're using is a Gaussian process. And the Gaussian approximation potential framework also uses Gaussian processes. They do use a sparse GP, which is a little bit different from what I'm presenting, which uses sort of the classic exact Gaussian process. But yeah, there's a ton of similarity in our approaches. So thank you for bringing that up.
Okay, so good to know that they're not like exact synonyms, but kind of from the same family, perhaps.
Yep.
Thanks. And we also have a question from Shraja Mukherjee. Would you like to ask your own question? Your microphone is now working.
Thank you so much. I'm so glad I could find a spot for this amazing webinar. So I have a very naive question, like for when you're trying to pick the plausible values for hyperparameter, like can you do some sort of iterative, can you take some sort of an iterative approach where you can try multiple values so that like you're not limited to what we are not limited by what plausible values we provide?
Yeah, that's a good question. So what I presented was basically like vanilla gradient descent, where you choose an initial seed for the optimization, and then you fall into whatever local minimum you happen to fall into, which might be an issue. Like there's no guarantee when you're doing hyperparameter optimization that there's exactly one minimum. It's not like a convex optimization problem. So you know, exactly as you suggest, it might be smart to sort of do multiple initial seeds and try to take the best numbers that you land on. That would be one way of addressing this problem of the possibility of multiple local minima. But yeah, that's a good point, and it's definitely a good strategy.
Thank you, Jonathan.
Thanks.
Okay, we have a question coming from Hosam Farak. I just unmuted you, Hosam. Oops.
Hello, can you hear me now?
Yes.
Yeah, thank you. So I have a question concerning how good is this framework working for molecular systems? Is it doing a good job as well, or not? And
that's a great question. Sorry, did I cut you off?
Yeah, I have a follow-up question concerning the same line. So let me ask as a question as well. So, and how good is it doing for Coulombic systems, like having long-range interaction? You are imposing a cutoff on your training set in your kernel thing. So yeah, these are my questions.
Yeah, both really good questions. So for molecular systems, what we're finding is that it's important to introduce a many-body component to the force field. So 2 and 3 body often doesn't give you the best performance. You need some more sophisticated kernel to actually, you know, model molecular interactions with the best accuracy. So basically, you need to go a little bit beyond the 2 and 3 body kernel that I'm presenting here. But there are ways to do it, and it's kind of an active area right now to extend these approaches to complex molecular systems. Especially when there's, you know, both solids and molecules interacting with each other in the same simulation. That's sort of a very open, interesting area. Regarding Coulombic forces, yes, that's also a very important issue. So what I introduced is this sort of strictly local model where we're not explicitly modeling long-range forces. And there are possible approaches you can take to introducing the Coulomb force to your force field. You can assign, for example, partial charges to the ions, and then add on the Coulomb force to your force field. but trying to learn how charge actually transfers in the simulation is tricky to do. You basically need some time dependence in your assignment of partial charges, and doing that properly is sort of an open problem that a bunch of different people are investigating. So yeah, two great questions, and they're both sort of open areas that that are being investigated.
Awesome.
Okay.
Thank you. The next question comes from Wang Suk Jung. I just unmuted you.
Thank you. I'm Won-Suk from Seoul National University. And does your model learn the DFT forces directly, or does it learn DFT energy and then gets forces by differentiating the energy?
So we learn forces directly. Basically, we do that by defining a force kernel. So we take the kernel here and we take the derivative of it to give us a force kernel, and that allows us to learn directly from forces. And typically that allows you to learn these force fields much more efficiently than if you train just on energies. So force information can give you a much richer set of information about the potential energy surface. Okay. Yep.
I think it is okay when you do the ND simulations, but without the energy, you cannot do other calculations such as defect energy calculations or surface energy calculations. And even with the MD simulations, I think the energy might not be conserved when you use only the forces. So I think there might be a drawback.
Yeah, so that's a great point. Energies definitely are important, and you can train on energies as well in this formalism. One thing to note, when we do train on forces, the forces are expressed as a derivative of a global energy. And so the force field that we learn is exactly conservative. So there's no issue with energy conservation. As long as you're careful about defining the kernel, the force kernel, to be an exact derivative of an energy kernel, you end up with a conservative model. So I'll open it up for questions at the end. I do want to get to the last half of the presentation, which touches on active learning and on-the-fly learning. But thank you for all the great questions so far.
Just one more question, if you don't mind. We do have a hand raised from Yan Gota. Sorry.
Yeah. Hi, Jonathan. Could you hear me?
Yep. Just briefly. Yeah.
Yeah. So I have this small question that for better training, do we need to have more AIMD data with different temperature and volume, or is just one data would be sufficient?
So that's a great question. It depends on what you're interested in simulating. So for example, if you're interested only in a particular pressure, then an AIMD simulation that's roughly at that pressure is often sufficient. As for temperature, so basically you want to make sure that the training data is at the temperature you want to simulate or above. If your training data is below your target temperature, you're going to run into some issues where basically you haven't sampled the phase space that you're trying to simulate, and so your model isn't going to give you good results. So it is important that the training data sort of resemble the simulation that you're ultimately interested in if you want to get good performance.
Yeah, I have just another small question. How good this 2 and 3 body kernel are for modern solid electrolyte, where you will have polyhedral network and the sodium or lithium species are in between that?
So I think I might have missed part of the question. You're asking how? Yep, go ahead.
How, I mean, to say that how good the model is, I mean, 2 and 3 body kernel for a material where you will have polyhedral network plus diffusing ions.
Yeah, that's a good question. So at the end, I'll show you some data on a somewhat similar system where basically we did big simulations of this silver iodide system and saw correct modeling of silver diffusivity in the material. But I will say, if you try to push it to really complex systems, it's important to sort of introduce many body effects into your kernel. But it's hard to say sort of a priori how well a 2 and 3 body model will do. You kind of have to test it and check. And if the performance isn't acceptable, then you need to sort of make your model more complex.
Okay, thanks.
Okay, and with that, maybe let's move on.
Okay, great. So the last portion of the notebook is now going to be on active learning and trying to automate the process of learning a force field. So typically you would want to do this with some kind of DFT code like Quantum Espresso or VASP, but that's sort of tricky to compile in the Google Colab environment. So what we'll do is just define a fairly simple energy model, so the Leonard-Jones force field, and try to reconstruct it on the fly. So Leonard-Jones takes this sort of simple form where you have a contact term that goes as 1 over r to the 12, which makes sure that the atoms don't get too close together. And you have an attractive term that goes as 1 over r to the 6. So the derivative of this is what gives you your forces. Okay, so the derivative of that potential with respect to atomic separation looks like this. So what we'll do now is define a sort of custom DFT module that's just going to return Leonard-Jones forces. In the Flare code, you can define a custom DFT solver like VASP or Quantum Espresso. Here we're just going to make it as simple as possible. So let's run that block. And now this block of code is going to define a particular kind of arbitrarily chosen Leonard-Jones potential, which is defined by this epsilon parameter and the sigmas. Okay. So let's set those. And just to show you what it is that we're trying to learn, this is essentially going to be our ground truth. This is the Leonard-Jones potential that we just defined. And the goal is going to be to train a machine learning model on the fly that reproduces these ground truth curves. Okay. And basically it's telling you what is the force on the atom as you separate the dimer. So to do this on the fly learning procedure, there are basically a couple of steps we need to go through. So basically, we need to first initialize a structure. So here, what we'll do is just create a BCC unit cell. So this defines the positions. We'll make a supercell of 3 of these unit cells. We'll jitter the positions of the atoms to make sure that the forces are non-zero in the first frame. And let's view this initial structure. Basically, it looks just like a BCC structure with the atoms slightly perturbed. And this is going to be the first frame of our on-the-fly molecular dynamics simulation. The next step is to set up a GP model. This is similar to what we did in the first half. So because it's a Leonard-Jones potential, we can get away with just setting the kernel to be a 2-body kernel. And so here we'll just initialize the GP parameters. And the third step before we actually run this on-the-fly learning procedure is to set up this training object. So we specify things like how many steps do we want to take in the training simulation, what is the time step. Here we'll set it to be a femtosecond, so the time is in units of picosecond. The tolerance factor is an important parameter in this training. It basically says if the GP uncertainty goes above this value, then we're going to make a call to our reference solver, which in this case is Leonard-Jones. If it's negative, that means that this is going to be an absolute value. So whenever the uncertainty goes above 10 millielectron volts per angstrom, we're going to make a call to the reference solver. If it were positive, then this would be interpreted as a fraction of the noise parameter of the GP. So in this case, 10 MeV per angstrom is a reasonable thing to choose. We specify which atoms we want to put in the GP training set on the first frame to sort of initialize the model. We set the max number of atoms that get added when new data comes online. And finally, we have a parameter that sort of freezes hyperparameter optimization after a certain point. And this basically reflects the fact that once you have enough data, the hyperparameters typically do not change that much. And in the training run, just to get a flavor of what active learning allows you to do, we're going to rescale the temperature of the simulation at step 10 to be 1000 Kelvin. So basically, we'll start at a low temperature, and then a few steps in, we're going to rescale the temperature and check if the Gaussian process is sensitive to this new phase space that we're entering. Okay. So that initializes the training object, and now we're going to just run it. And so basically, this will take a couple of minutes, but it's doing this fully kind of automated on-the-fly learning procedure where, whenever the uncertainty is too high, we augment the GP training set with new data. And what you'll see if you open up the files section of the notebook, there's now an output file that's being generated. I'll just open up the output file now to show you what it looks like. Okay. So the first part of it shows you, how many CPU cores are you running? How did you initialize the GP? So our cutoff was 5 angstrom with a 2-body kernel, and our initial hyperparameters are these values. And we have our previous positions here, which is our randomly sort of perturbed BCC supercell. And this is the start of the actual run. So we make an initial call to DFT, or to our reference solver, and we get the forces on the first frame of the simulation. So here in these columns, we're seeing what those reference forces are. This is ground truth, so the uncertainties are just 0. And the GP model now gets augmented with this first batch of data. And then we make a step with the Gaussian process model. So frame 1 here is being generated with the GP. So we have listed here what the GP predictions are, along with their associated uncertainties in EV per angstrom. Okay, and you can see most of these are well above the threshold that we picked, 10 MeV per angstrom. And so the model is going to basically request more data. So it's going to make a call to the reference solver. It's going to get the true ground truth forces on all of the atoms. And then it's going to augment the model and re-optimize the hyperparameters. And then we just proceed in this way without really any intervention. The model takes a step on its own. It checks the uncertainties. And if they're too high, it augments the training set of the model. And it'll keep going until essentially the GP has requested enough data and it's able to run on its own reliably. So now, if we go back to the Colab notebook, we'll see that the run finished. So we can now parse the output file and take a look at what happened. So this block is now showing you the temperature of the simulation as a function of time. And the black X's are calls to DFT. So you can see initially, we need a fairly small number of calls. The model runs on its own for a while, and the temperature gets rescaled here at step 10. And so after a little bit of time, the atoms sort of enter this sort of new region of phase space. The uncertainties go up, and we need additional calls to DFT. And this is kind of the active learning picture that we typically see. If you randomly sort of rescale the temperature to something bigger than the model has seen before, you need new data, and the GP uncertainties tend to spike. So as a final step, we can take the model that we just trained and compare it to the ground truth forces, which is Lennard-Jones. So this block of code will do that for us. Okay, so this plot is showing you the predicted force as a function of the separation of two Lennard-Jones atoms. And you can see the solid lines here are our ground truth. So this is the correct behavior of the Lennard-Jones potential. And the dashed lines are what our model is predicting. And I've also included some error bars showing you what the GP uncertainties are for this range of separations. And what we're seeing basically is that in the particular simulation that we just ran, there is sort of a narrow range of distances that the GP saw. And in that narrow range, the uncertainties are quite low. As you move away from what the GP has seen, the error bars get pretty big, and also the deviation from ground truth gets pretty big. So what's good to see is that as you move away from the training data, the model performance goes down, but it's sort of aware that it's going down. It has high uncertainty for those values, which is sort of a good sanity check that the Gaussian process uncertainties are working the way that we expect them to. So just as a final couple of words about some of the things that we've applied this to so far. Here is a simulation that we did for silver iodide in a sort of three-step process where we started at fairly low temperature and then rescaled the temperature of the simulation at several points. And you can see, every time we rescale, we need to make some new calls to DFT to update the model. What we did was we took the resulting model from this on-the-fly simulation, which is quite similar in principle to the one that we just did. And then we used the model to do fairly large-scale molecular dynamics simulations. So in this example, for this system, there's an interesting phase transition that happens around 420 Kelvin. And we were able to correctly model the transition from the low temperature HCP phase to the high temperature superionic cubic phase. And also we saw quite good agreement between the sort of machine learning driven molecular dynamics simulation, which is shown in blue, and both AIMD, which was much more expensive and done on sort of a much smaller length scale. And also with experiment, you can see the activation energies, which are given by the slopes of these curves, are in quite good agreement. So basically, this opens the door to doing molecular dynamics simulations of interesting sort of materials that exhibit, non-trivial phase transitions and sort of interesting diffusivity properties. And we've looked at, a range of systems at this point. So, this kind of method can work well for things like 2D materials, fairly simple solids like carbon and silicon, even, alloys like nickel titanium. It seems to perform reasonably well. And so with that, I would like to thank you for your attention and point you to different resources that we've put online. So the paper is open access. If you're interested in what I presented, I encourage you to check that out. And the code is all open source, and we're working on getting it reasonably well documented. And this is kind of the Flare team, everyone who's contributed to this project over the last year or so. And with that, I'd like to thank you for your attention, and I think we have a couple of minutes for questions.
Okay, so thank you so much. I think we have some raised hands, so let's take a quick look. Let's see, Jung again. Let's see if I can unmute you.
It's Won-Seok from Seoul again.
Okay.
So active learning seems to apply only to the small systems that the DFT can handle, but it is quite common that everything looks fine for small systems, but when you simulate for the large system, then unexpected failure occur. So for example, I imagine when you want to make a validation out of the 10,000 atom silver iodine simulations and found something wrong, it cannot be actively run by your algorithm. So can you make the comment out of it?
Yeah, that's a great point. And this is sort of an important open area for active learning. How do you apply these types of techniques to really big systems that DFT can't handle? So, if you have some 10,000 atom system, you can't evaluate the DFT forces for that whole structure. You need some other approach. One thing that could work in principle is you sort of use your Gaussian process uncertainties to flag regions of the large structure that are highly uncertain. And if you can sort of remove that piece of the bigger structure and put that into DFT and get forces on those atoms, you may have a way of sort of extending this type of method to larger systems that can't be treated completely with DFT. Another point on this question, it's a great question. One thing you can do to sort of validate the performance is, you train on a small structure, you try applying the model to a huge structure, and then you look at the uncertainties on the large structure, which are possible to evaluate in a reasonable amount of time. And you can see if you've sort of entered patches of phase space that are unfamiliar to the model. This at least allows you to check if you're kind of outside of the training set or not. But then you have this issue of how do you actually get good reference data on this bigger structure? And that is sort of the interesting, difficult challenge.
Okay, thank you.
Okay, so I think that was our last question. So once again, thank you for all of our attendees and all of our panelists. We will be announcing our...
We have one more question, if you don't mind.
Oh, wait, we have
I
another
see
one
a
that came
raised
up?
hand from Elizabeth Lee, and I'm just unmuting her right now.
Okay.
Let's see there. Elizabeth, if you can hear, you're unmuted, and please feel free to ask a question.
Oh, hello. Hi.
Yep.
A great talk. I was wondering, all the examples you have shown, especially for the ab initio MD learning part, seems like it was done on solids. I was wondering if your group has tried machine learning methodology for a non-periodic solid to generate on-the-fly force field.
Yeah, great question. And actually, that's an area that we are quite interested in. So let me quickly go up to, oops, if I can, to this catalysis system. So this particular example is also sort of an extended solid that's fairly simple. But what we're quite interested in is what happens as you start introducing problem quite a bit trickier.
Jonathan, I think you're breaking. I could only hear you remotely.
Oh, sorry. Can you hear me now?
Yeah. Yes.
Yeah.
Yes. Much better. Thanks.
Okay. Yeah. So I was saying we're interested in what happens as you start introducing adsorbates into this type of system. So if you put a molecule close to the surface, you start getting some tricky interactions between the metal and the adsorbate. And this is something that we're sort of actively pursuing. We're finding that 2 and 3 body models aren't quite good enough, aren't giving good enough accuracy. And so we're exploring ways of extending this approach to more sophisticated many-body kernels. But to answer your question, yes, it seems like it is possible to extend this to sort of more challenging non-periodic systems. Basically, the same principles apply where you only consider local environments around the atom. But it does seem to be possible. You just have to use the appropriate machinery to get good model performance.
Thank you.
Okay, let's see. Do we have any others, or are we out of questions? Let's see. Is this question still active from Shadra?
No, my question is answered. Thank you so much.
Okay, so I think that's everything. So thanks again, and please join us for our next please join us for our next webinar. We'll see you then.